monopole, and we covered the dipole. 7.2.5, this is it a monopole or dipole?
I asked for, let me pull it up, asked for the voltage standing wave ratio, which we haven't.
VSWR. Yeah, we can do that real quick. So if the, and here, this is the VSWR. This is from EMAG 1, if you remember that. The standing wave ratio is what? Well, it's 1 plus the magnitude of the reflection coefficient at the load over 1 minus the magnitude of the reflection coefficient in the load. It's the voltage standing wave ratio.
The lossless 50 ohm coaxial cable.
All right, 50 ohm. All right. Remember this always. It's the impedance you're going into minus the impedance you came from over the sum of the two, right? Now, here, I'm assuming he's using an exact half-wave dipole, and I think he is. And that would be what? 73 point, so in other words, let me just put it to you this way. Z load itself, you guys tell me what you get. It's going to be 73.2 plus J 42.5. Do you all agree with that, class? And if Z naught is 50, what do you get? So now come over here, what do you get for your VSWR? 2.18.
The transmission line length is 1/3 lambda. Determine the total average power radiated by the antenna.
So we've got this kind of thing, and we have a voltage source, plus or minus VS. Now we've got the transmission line, right? And I've got the load here, and the load is going to be 73.2 plus J 42.5, right? And there's a couple ways to do this. Characteristic impedance here, Z naught is what? 50 ohms, right? You agree? Is that transmission line loss?
Yes.
Yeah, it is. All right, now, here's the thing. At some point, they're asking for the total radiated power. What tells you what's radiated? But it would be 1/2 I squared, magnitude of I squared, times radiation resistance. That's the radiation resistance, right? This is a transmission line. We know the length of this thing, L, is equal to lambda over 3. I think you said that, right? Now, what do you know about Zn here?
It's 1.3 lambda.
Zn is equal to, what did you say? 1.3?
Lambda.
Does it matter if it's 1.3 or 0.3, class? I'm getting at something. You remember how every time you go half wavelength on a transmission line, you can basically remove that segment if you're just looking for the input impedance, current, anything like that. You all with me? Every half wavelength, everything repeats itself. If it's 1.3, get rid of the 1. It doesn't matter, just 0.3. What is Zn for a transmission line right at the input? So this is Z naught, then it's going to be times the load impedance. Remember, the load impedance is real and imaginary. It's got 73.2 plus J 42.5. Then it's plus J, and it's going to be Z naught times the tangent of beta L over Z naught, right? Then it's going to be plus J ZL tangent of beta L. Let's look at something here for a second. The value beta L becomes important in this one. So beta is 2 pi over lambda, then it's times the length. Now you can put 1.3 lambda there, but I would recommend you subtract off stuff. So this is lambda over 3. So this is really going to be 2/3 pi, right? Well, 1/3 pi is 60 degrees. 2/3 pi would be 120 degrees. You're going to need that. So we got tangent of beta L. Well, it could equal tangent, if it's in radians, of 2/3 pi. That's opposite, or sorry, y over x, and this is 60 degrees. Minus the square root of 3, is that right? Okay, I'm going to go with it. Is that right?
That's what I get.
That's what I got.
I need the value for Zn. This equals 22.97, go ahead.
Minus J 2.1856.
2.1856 ohms. Anybody get that or confirm or deny that? And we'll show you a trick. Anybody? Y'all get that? How many got it? Now, while you're getting, just make sure you get that. Now I'm going to show you the equivalent problem and how what I've done in the past, and I wish I didn't do it, but what I've done in the past I go ahead and get this impedance. Now here's what the circuit looks like at the base, right? I got a voltage here, plus to minus, and I got V load. What is V load for this one
But
again?
100 volts, root mean squared.
100 volts and it's RMS, right? So if we multiply by square root of 2, now it's peak. And I'll call it V load and put peak down. But you can do it with RMS stuff too, right? Now we've got this impedance. Now the impedance, right there for everything, transmission line and load, back at the thing that's going to limit the amount of power, is 22.97 minus J 1856, right? Now, listen to me. How much current is flowing here in magnitude only? Okay, this is going to be magnitude VL, or it's square root of 2 times 100, and I got it out of RMS, put it in peak, because usually our problems have peak values. If you're in power, with Dr. Gross especially, it would be RMS, but you have to know the relationship. So I have that as the voltage. I forgot to account for, I didn't even know there's a source resistance.
20.93, yeah.
7.3
Yeah.
amps. That's a lot less. What'd you get for Z in over here? That's needs to be exact.
Why would you use the
All
same
reds.
radiation?
73.2.
Huh?
Why do you use the same radiation?
Oh, God. You know
Yeah,
what?
shouldn't it be ZN?
It is. It's got to be.
The real
Sorry. Take. Idiot. Take the real part of this. God, God. This is what
It's
happens.
gonna be like 23.34.
22 point what?
23.34.
I'm sorry. I'm very sorry. This should be 23 point what?
23.3458
Plus J what?
plus J 6.106.
Okay. It should be this. I'm so sorry about this. So that's my fault. So it's 23.34, and that should give you the right answer. Do that.
I get 42.5.
What do they have?
I mean, yeah, 42.5. They have 43.1.
How much you want to bet there's a round off error somewhere? But here, I'm sorry, the way I've typically done this problem, I'd find the voltage here, V prime, then I'd get V0, then I'd calculate V load, then I'd find the current, then use that times the rate, 1/2 I squared times the radiation resistance. You don't need to do that. You can just do it right that way. That was the whole point of that problem.
Would there be, this having to do with waveguides, but you mentioned there may be one where you have to match a waveguide to a source as well?
Well, it doesn't have to be, this is not matched.
Right.
But if you're gonna match, you're talking about matching impedance?
Yeah, right, that was for waveguides, all right.
If you want to match impedance, then you're going to have to add an element here, right? A waveguide, remember, waveguides
Right.
have characters, but if you want to match this, then it's basically going to be something where you would have to add, either in series or parallel, just like we do with transmission lines, either an element like a capacitor, inductor, or a stub, shorted, or just like we would. All right, that's for matching. Now that's different. And it's trickier too, because if we match, what happens? If it's matched, then that means this looks like 50 ohms, right?
Right.
If it's 50 ohms, it looks like 50 ohms here. And if it's 50 ohms, it's 50 plus 50 is 100 divided into 100 square root of 2 is just square root of 2, right, amps? Follow me? The real part is just 50, so you take 1/2 times square root of 2 squared times 50. So it's really going to be 1/2 times square root of 2, right? And that's going to, I mean, I don't want to go down that route too far, but it becomes a much different type of problem because it's matched.
Okay.
This is not matched. Problem 7, go ahead. Point,
2.2.
and go ahead.
A lossless quarter wave monopole antenna.
Okay, hold on for 1 second, got a lossless. And this is a quarter wave monopole, lambda over 4 monopole. Go ahead.
Is situated above a perfectly conducting ground plane and is driven by a 100 volt, 300 megahertz source.
RMS?
It doesn't say.
it should be V RMS or V.
Just the,
That's peak then. I mean, typically, and normally that's assumed peak unless it says RMS. Go ahead.
300 megahertz is a frequency that has a source impedance of 50 ohms. Determine the total average power radiated. Also determine the magnitude of the electric field broadside to the antenna.
Okay. So this is the actual sketch of the problem. Now I'm going to show you the equivalent circuit. For this one, we have a plus or minus V equals 300 volt source, and I'm assuming that's peak. Then you have 50 ohms. These are called lumped element models. They're just resistors, capacitors, and inductors that model the circuit so you can get the actual values, either current or voltage that you need. That's a monopole, so it has 73.2 plus J 42.5 divided by 2 ohms. Y'all with me? So the first thing we're going to get is the current through here. So what is the current flowing through there? Well, it would be 300 over 50 plus that, which is 73.2 plus J 42.5 over 2. And I need that current.
Voltage is just 100 volts.
Oh, I got 300, sorry. Another sip of coffee. My bad.
And 100 on top. 100 volts.
Oh, yeah, 100, sorry, thank you. What did you get? And now, what did they ask?
Determine total average power radiated.
Okay,
Also
guys.
magnitude.
I want to ask everybody just to consider, how would you figure out the total average power radiated? Radiated. Is any radiated power associated with that 50 ohm? Any power radiated associated with the J42.5? No. Only what? Only the 73.2 divided by 2, right? So to get the total power radiated, now this is assuming that this voltage is in peak. If it's not, we're going to have to multiply this by 2. This will be equal to 1/2. Then it's going to be that I squared times R rad. So that's going to be 1/2 times magnitude of 1.12 squared times R rad. And R rad for that one is 73.2 over 2. What do we get for that? 22.96 watts, right? Correct? Okay. Now, what's the next thing? He wants either, now there's 2 ways to do the next part. He's going to ask for an electric field, right, at a certain range?
Yeah, like R.
Does he ask for a power density too at that range or not?
He does ask for power density. Yep.
I'm going to tell you the way I would do it. And you're free to do it the alternative way with the E-field thing. I wouldn't do it this way, but I'll just show you this. Remember what the electric field is for a half-wave dipole. It's equal to what? It's equal to J times 60, right? Times I. That's the current we calculated. Then it's divided by R. Right? Now, I'm going to look just at magnitude. Then after that, we know there's an e to the j beta r, but we don't care. I'll put it here, e to the minus j beta r. That's a phase term. I'm going to put a magnitude on it. Then it's times that angular function. Now, even though it's this quarter wave monopole, the actual pattern will be the same as a half wave dipole with that current. Y'all with me? So the pattern angle, the angular pattern is going to be cosine of pi over 2 cosine of theta all over the sine of theta. Can you follow me on that? What is the angle and what is R?
The angle's 90 degrees.
Oh gosh, so this is 1. If it's 90 degrees, this angular function is 1. You with me, class? Everybody? So you can just replace this whole thing by 1. What is the range?
It's about 100 meters. Distance of 100 meters.
100 meters, okay. So if you do this, using this equation, it would be J60 times I, which is 1.12 divided by 100. And then that's it. So you just take as a magnitude, the J goes away, right? So what do you get? 0.672 volts per meter. That's one way to do it. Do you agree? Here's another way to get the electric field, but first I'm going to get the power density at that point. I can say the average power density at that point is P rad. We have that somewhere. Where's it? Right here, right? Then divided by 4 pi R squared. Now that's the radiated power density average, isotropic power density. Then multiply it by the directivity. Now, here's the caution. Remember, the directivity for this is twice that of a half-wave dipole. Radiation resistance is 1/2. Do you all remember this? All right, so I'm going to take this, and it's going to be 2 times 1.64, right? Now, there's that angular function that I crossed out because it's 1. It's going to be that same angular function squared. Y'all follow me? Well, if it's 1, who cares, right? So this would be the average power density. Can you give that to me? The P rad here is 22.96, so I just need the power density. And R is 100, so it's divided by 10,000.
Is that also, I saw in the one note you gave it as gain, so that's also.
Gain is
PRAD.
directivity if I don't put, if I have nothing said about efficiency, you assume directivity and gain are identical. 599 microwatts per meter squared. Now, that's the power density. What am I going to do to get the electric field from that, assuming it's free space? I'm going to say that power density, right, is equal to 1/2 magnitude of the E field squared divided by 8 naught. Am I not? Yes,
Can I
Brett.
just ask a quick question? Why are you, so is that 2 times 1.64?
Yeah, do you know what the gain of a half-wave dipole is, or not? If you don't worry about it. All right. So the gain directivity of a half-wave dipole, and I'm going to say its directivity, assuming the efficiency is 1, is equal to 1.64. Then you're going to have that angular function, cosine of pi over 2 cosine of theta over the sine of theta, but that whole thing's squared. That's the way it comes down. That's for a half-wave dipole, right? For a quarter-wave monopole, you got to multiply this by 2. If you have a half-wave dipole's gain, and now that same antenna is used as a monopole, quarter-wave monopole, the gain goes up by 2, the radiation resistance goes down by 1/2, but the current is the same. That's the interesting. All right, now back to this thing. Therefore, what's the E field going to be? Well, the electric field magnitude at that same point is going to be what? It's going to be square root of 2 eta naught times P average, right? And I bet you it's that. I hope. Same thing?
Yeah.
Y'all understand it? Great problem. Is there another part to this or not?
What is the direction of the electric field vector with respect to the ground plane?
At what, theta equal 90? Okay, guys, this one you should know. Remember, it's a time-varying electric field. It's going to have positive, negative. The electric field, if you have anything, if this is radius vector R, the electric field in the far field is always in the theta direction, right? With me? Now, if it's at the ground plane, you can see how it's at what? It's just the negative value, negative z direction, right? Is that what he says?
Perpendicular.
All right, perpendicular, that'll work. But you all follow me? It's perpendicular to the ground plane. What I want to do is go through the Friis equation. I'm not going to do arrays yet. I want you. Friis equation fits naturally right here. It's an extension. Friis equation. And I'm going to tell you, there's a lot to this, but I'm going to get to the brass tacks. So you have an antenna 1. And I'm going to call this the transmitting antenna. And then you're going to have antenna 2. And this is the receiving antenna. And this antenna, transmitting antenna, has gain of the transmitter. Be a function of theta for this one. This is the receiving antenna has gain of the receiving antenna as a function of angle. Y'all with me? Now here's the game. We're trying to find out if this antenna is transmitting P rad. That much power is being supplied. It's radiating that much power. How much power is actually received by this? What is P received? So that's the question we're going to tackle. The first thing we're going to do is figure out what the power density is here. We want the average power density from this antenna at the point where the second antenna is located. It has nothing to do with the type of second antenna, just that observation point. A given radio distance away, given angular, either elevation and azimuth or whatever, the angular point. So that power density, this is your first part. The average power density incident there from the transmitting antenna would be the total radiated power divided by 4 pi r squared. Now that's going to be what? That's the average power density of an isotropic radiating antenna. Now you need to multiply it by the gain of that first antenna for the position theta, whatever it is, with respect to that point of observation r. So now it's going to be gain of transmitter, and I'm just going to leave it as gain of transmitter. We know we're going to change that depending on r and theta. Y'all with me? Really just on theta in this case, correct class? Now that's the power density incident there. Now what about this second antenna? Well, it's an interesting proof, and we're not going to have time to do it today. But this antenna has an electrical area. Put this down. So it, quote, quote, looks like it has an area A equal to lambda squared over 4 pi, and this is the receiving antenna, times the gain of the receiving antenna. Now, so the area, this is how big it looks. The units of that are meters squared. Lambda squared is the wavelength. Wavelength squared divided by 4 pi times gain of receiving antenna. I want you to catch this. So this receiving antenna, when it talks about the gain, it's the gain in the direction incident. By the way, the gain of if it was transmitting back to the first antenna, the angular function would be the same as receiving at the second antenna. In terms of this one's transmitting or receiving, the angle you want to get is this angle. That's the thing. So it's the gain at the receiving antenna at that angle. Now, I'm saying that for a reason. If this is a straight wire antenna, what's the gain when it's like this? Take it vertical and then move it so it's along the R direction. Class? Zero. It's got to be zero, right? Because the gain of any straight wire antenna is a maximum perpendicular to it, and it goes to zero when you're talking about the gain in the axis. In other words, no power is ever radiated in the far field straight up or straight down from a straight wire antenna. Never. You with me, class? Now that is the area. So when we want to talk about the power received, we can say P received here is going to be the average power density, or it's going to be P av times the effective area, the aperture. And this right here, I call it the area. It's usually the aperture, and a lot of times they put it as AE. This is called the effective aperture. Of the receiving antenna. Follow me on this? And it's going to have it's meters squared. The incident wave coming in has units of watts per meter squared. Oh boy. Watts per meter squared. Yeah. Ouch. Long story behind that one today. But anyway, This will work. So now I can say P receiving right here is going to be average power density. That's that. I'm going to put it on P rad, so radiated power density over 4 pi r squared. That's times gain of the transmitter right there times the aperture. Well, that's going to be lambda squared gain of the receiver over 4 pi. Can you all follow me what I've done here? I've just substituted in the values for average power density and the effective aperture area here. Now I'm going to get the ratio of the two. And this is called the Friese equation. It's in your book. P received over P radiated. So it's the ratio of the two. And what they'll do is they'll pull a lot of this stuff into one term and square it. So they're going to say this is going to be really gain of the transmitter, gain of the receiver. And Whitmore Spokie's going to have directivity, I think, but it's better to put gain there. And it's at the angles associated with it. Then it's going to be divided by lambda over 4 pi r squared. Can you all follow me in that? That will be the total power received. Now I've got to be clear about this. That power received is not the power available to a load. So if we put a load here, attach it to the actual terminals of the second antenna, the most possible power you can get out of that is half the incident power received. The other half is re-radiated. That's something that's not really it doesn't come out in Dr. Wentworth's discussions, but is so critical. Even though the antenna receives, say, 30 watts, the best we can ever extract from that 30 watts would be 15. And that's if everything is matched perfectly. Are you with me, class? It's a very important concept. All right, so this is called the Friese equation. I got to mention a few things about it. Sam Wentworth's book does talk about it. There's one big thing you have to be aware, because you can do stupid stuff if you're not careful. I'm assuming these antennas, when I start my discussion, that they're oriented in the plane of the board. You all with me? And I'm trying to show you this. So it's like, it could be like this, you know, it could be at some angle, but it's in the plane of the board. Now there's something that happens. Suppose they're broadside. If I start tilting the second antenna like this and it's a straight wire antenna, when it goes to 90 degrees, you receive nothing. You all with me? It's just like you're tilting it this way, all right? And the reason is the electric field will be oriented in this direction along the plane of the ground, if you might think of it that way, the horizontal plane. When this thing, the electric field's vertical. When it looks this way, it would like to measure the component of that electric field in this direction, but it can't. It's just not oriented that way. So there's a thing called a polarization mismatch you have to account for. And over here, what they'll do is say, it's times the cosine of something called tau, which is the tilt angle squared. Tau is the tilt angle. Now, I'm trying to just make you see this. Look at these two things. In line, there is no angular tilt difference, right? If I take this and I move it off 30 degrees, you all with me? It would be the cosine of 30 degrees squared. You all with me? If it moves this far, it's the cosine of 90 degrees. What's the cosine of 90? 0. You all with me? That's the way you think of tilt angle. And there's a couple things. If you're looking at this and I'm moving the second antenna this way, but it's not tilting, it's just staying aligned like this, then what will affect the gain is going to be the actual, you might say, how it moves in the plane of the board, if you can think of that. That will change the actual gain of the receiver. If it's aligned like this and it's up this way, but it starts tilting this way, then you multiply by a cosine of the tilt angle squared. You with me? Just things you need to consider. I'm going to show you how we actually calculate a model, and I'll do this on Wednesday, of that received power density so we can attach a load and see how much we can extract, okay? I'll do that on Wednesday. I'm going to give you some